All right, we're in Algebra 1. Today's date is Thursday, February 27th, 2020. We're talking about linear versus exponential growth data, and this is the final lesson for our unit. Yeah, we're down here at 8-9, then quiz, then test. So, our objective today is to do what? Is that a hand, Larissa? No? Okay, yeah, Emma.
Well, I was going to say I see an error. Where?
Yes. What's error?
Where?
Don't know.
It says
Whether?
It says determine whether data.
Oh, yes. Yeah, that is a typo. Yeah, log it. I'll fix it for next time. Thank you.
I don't have notes.
Oh, weird. You can take Jade's. You can just erase her name. I don't know. That means there's another thing of notes floating around somewhere. Oh, do you mind switching with Wyatt? Cool. So, you've seen this almost the exact same type of tables in the very first lesson, and now I'm kind of closing with the same type of notes. One of these is linear, one of them is exponential. That's the whole idea behind this unit, is not only to learn about exponential equations and functions, but to compare them with linear. So one of them's linear, one of them's exponential. Do you guys remember all the way back from 8-1, which is probably 2 or 3 weeks ago now? How do we tell the difference between the two? One of you knows, 2 of you know, 3 of you know, 4 of you know. How do you tell the difference? Which one is linear, which one is exponential? Ulysses, talk to us.
Like, for the first table, it's like, for x, it's adding 2, and then for the bottom, it'd be adding 4, and then that'd be in there. And then for the other table, it's like adding 3 and then timesing by 2 on the bottom.
Timesing by 2, so multiply by 2. Everyone have this in your notes too, please. Multiply by 2, and I guess I can zoom in so you can see this a little bit easier. And multiply by 2, and you said you were adding by 3 on the top. Thank you. Plus 3, plus 3, plus 3. Yeah, so that's the great pattern. And then Ulysses, what does that mean?
It's exponential.
Which one?
The second.
Okay, yeah, so we'll say this one, we'll label it exponential. And this one is going to be our linear. Cool. Yeah, so just as our quick little review, adding in terms of y values for linear each time by the same amount. You're adding by that common difference over and over again. And exponential, you're multiplying by that factor every single time. Multiply by a factor of 2, a factor of 2, a factor of 2. All right, no questions up to here. This is a good review. Let's also review the equations. Can someone give me the general form of an equation? That means with variables like a, b to the power of x, stuff like that. How do I do a general equation for a linear function? Start with linear. Yeah, Charles.
It would be a plus b times x, t or x? Or
Whatever you want to
a
call your
different
difference.
variable than a or b.
A times b, yeah, x. And b in this case is what? We'll give it to someone else. What is b, Ugo? Ooh, careful. So it would be the factor if it was an exponential. It has a slightly different name, and you can kind of look ahead, probably tell what it is. Yeah, it's the difference. Someone else. What is a? Asha?
A is the initial or the start amount. Initial or start amount.
Initial or start amount. Yeah, thank you. And then x is that variable that tells you how far to move forward. Perfect. Can someone give me the general equation for an exponential function?
Oh, I don't have my card anymore, but
I have a card.
You have a card, Wyatt? Yeah, Wyatt.
So the general equation for the exponential form is a, well, y equals a times b to the power of x.
Perfect. Yeah, there it is. And then another quiet raised hand. What is b? Larissa. Factor. And another quiet raised hand. What is a? What is A? Yeah, Eamon.
It would be the initial as well.
Also the initial. Thank you. Oh, and I very much messed up. I was supposed to make this an easy problem. Here, I apologize for doing this, but it does make it easier for us. Can we change these all, like shift them back to value? So make this 2 into a 0, make that 4 into a 2, make this 6 into a 4, make this 8 into a 6. I'm sorry about that. I meant to make that change. I made it for the exponential, but I forgot to make it for the linear. On Khan Academy for this assignment, they make them all really easy like this. I mean, we could have solved it finding the initial amount using the harder table, but I'm going to give you an easier table. So there it is, 0, 2, 4, 6 instead of 2, 4, 6, 8. Still adding 2 each time. Can someone tell me what the initial amount is for our linear? It's y equals what? What is this a value? Is there anyone that still has their card out there? What's our a value? Kira.
Y equals 8.
Say it again.
8.
8, yes. 8. And how'd you get 8?
Well, x equals 0 when y equals 8.
Yeah, that's where x equals 0. Cool. And then we can say, as a note here, that's where x is equal to 0 for our a value.
Should it really be a equals 8?
So you're saying a is equal to 8?
Well, isn't it?
Yeah, it is. Yeah, so we're just rewriting our equation now. So we're saying 8 plus, then I have to figure out what the difference is, and then I'm going to multiply that by x. I'm writing the equation of this table, assuming that it is linear. Can someone tell me what the difference is? We've already written it down somewhere. Is everyone in? I think everyone is in. No? Okay, Emma, it's you then. What is the difference? In terms of the y values, how much are the y values changing by?
They're changing by 4, so the difference will be 4.
There it is. The difference is 4, and therefore our equation is y equals 8 plus 4x. Done. Thank you, Emma. And now everyone's in. We can all participate multiple times. I know I accidentally called a few of you multiple times. Oh, Hazi? Oh, okay, Hazi, you have to do this next one. Are you ready? So I'm setting up this next equation where I have to get my initial amount. What's my initial amount for my exponential equation over here, Hazi?
2.
2. Yeah, how'd you get that?
You get 2 plus x is equal to 2.
Yeah, perfect. And I think now is everyone in? All right, cool. So times what to the power of x? Times what to the power of x? Ulysses? Times 2. Done. All right, so we're going to be making... What's up?
I found 10.
Found 10.
I found a 10.
Oh. And now 11. Cool.
Oh.
Thank you. All right, so this is kind of new material now, and this is where it gets kind of hairy and tricky. So finding differences in factors from a table, it's not as easy as just saying, oh, well, the factor is 4, because I've lied to you, and I'm sorry, I've misled you. This 4 and this 2, that's not quite true. So if you want to, you can go ahead and cross it out if you want. That's what it should be, but I'm lying to you, because what we're really doing is we're stepping by 2 each time. This 2 up here is going to change this 4 into something else. This 3 up here is going to change this 2 into something else. So how do I do that? Well, whatever this number is, if it's jumping up by 2, the x value is changing by 2 each time, then this is going to be 2. If this was jumping up by 7 each time, this number would be 7. In general, this is always going to be your change in x. And the way that we say change of x in math is we say delta x. It's your change in x times your difference. Yeah, what?
So is that for linear too?
This is only, whenever you're looking for the difference is only found from a linear function. And then we'll talk about exponentials with this equation right here. Yeah, good question. All right, so we have one side of the equation filled in. Let's do the other hand, or the other side, and this is going to be the delta x times the difference is going to be equal to this change in y. So delta y. So if you actually want to find what the difference really is, we'd have to solve for the difference. So I'd have to divide by delta x, and I would say the difference is equal to delta y divided by delta x. So I can come off here to the side here, and maybe I gave too much away by saying that. But I can say that the difference, I'm going to abbreviate here and say diff, is equal to, all I'm doing to both sides of the equation right now, I'm dividing both sides by delta x, divide by delta x, and therefore difference is by itself, and it's equal to this delta y divided by delta x. Question, Kira, go.
Yeah.
Why didn't you always do the change in x? That's what it's supposed to be.
Because we never had to find an equation before, but now that we're being formal and actually finding an equation, we have to be very formal about what we're doing. We have to make sure that we're accounting for the fact that we're jumping by 2 or 7 or whatever's happening with our x's.
So we're trying to find y, but we weren't trying to find anything before.
So before I just asked, is this linear or is it exponential? And you said, it's linear and it looks like a line, and you got it. Now I'm going to say, is it linear or exponential? And you'll answer the same thing. Oh, it's linear. And they'll be like, now tell me what the equation is. And that's where we have to get this. But this doesn't work. 4 is incorrect. That's not the difference. That's not the slope. You guys see the connection between the slope is the coefficient of the x for our equation. Check out our formula that we just have. Delta y over delta x, does that feel eerily familiar? Yeah, it's slope. So this number is going to be your change in y divided by your change in x.
So for that equation, would it be 4 divided by 2 to get 8 different?
Precisely, yeah. So we have our delta y was 4, so everyone can write it down over here as well. Our delta y was 4, and our delta x, our change in x, was 2, so I can say divided by 2, and therefore our slope, or our difference, was 2. What this value should have been was a 2, and then we would have gotten it correct. All right. And that should feel kind of reviewish because you've seen slope before. This is where it's like really, really brand new. How do we find the factor? And now we have to use some rules of exponents. So very similar to the thing that we had before, it's going to be factor to some power. And anyone want to take a guess as to what I'm going to put in this box here? Emma?
X?
Almost. You have to do the whole... What do we call this symbol?
Delta.
Yeah, so full thing is going to be
Delta x.
delta x, exactly. Factor to the power of delta x. And I'm hoping you're lost. Or maybe you're not lost and you're just really brilliant. You're like, oh yeah, that makes perfect sense. To me, when I see that, I'm like, why are you doing that, Mr. Sindel? I really want to connect what's happening in this equation to the table. So let me back up. Let's talk about the difference. If I jump twice, I guess if I'm jumping just once, I'm really jumping twice. I'm going 2 to 3 to 4. So if I were expanding my table, I would have 2, 3, and 4, where I know 2 and 4. 2 goes to 8. 4 is to 12. And I don't know this missing value, but I know I'm jumping once and twice. So how far have I moved? I've moved a total distance of 2. That is my change in x. So I'm changing in x by 2. But what am I doing each time? I'm adding 2. Add 2 is the same thing as multiply by however many steps I took. And I still see a lot of confused faces. So if I take 1, 2, 3, 4 steps, then I can multiply by 4 instead of adding and adding and adding and adding. Repeated addition is multiplication. That's why I'm multiplying by a number here. Now this is a little bit different. So if I'm stepping in the table, I'm not adding, I'm repeating my multiplication. Repeated multiplication is taking a power. So this is now going to be to the power of something. I'm going to multiply by a factor, multiply by a factor, multiply by a factor. How many times? Well, I have to multiply by a factor 3 times to get from here to here. It looks like I only had to do 1 step, but there's really 3 steps happening here. 1, 2, 3. So to account for the fact that we had to multiply 3 times, I have to do it to the power of 3. Or if I want to jump even further, 1, 2, 3, 4, 5, 6, to get from here to here, I would go to the power of 6 because I'm multiplying 6 times. Again, repeated multiplication is taking a power. That's where this is coming from. And if you're still lost, that's okay. This is a formula and it will work if you can just memorize it. Yeah, Charles.
Isn't the top addition?
So the top is addition. Yeah, I agree that the top is addition, but in terms of the bottom is the y value. That's what we're after. We're trying to figure out how these y values are changing. What is the factor? And the way to figure out the factor is you're going to be multiplying over and over again. All right, so question. Yeah, why?
So to like find the factor, is it kind of like the difference where instead of multiplying you divide, so it would be square root instead of like a power?
You're really, really close. You're half correct. So if I was jumping by 2 each time, yes, it would be taking the square root. But if I jump by 3 or 5 or a different amount, then you'll have to do cube root or fifth root, or exactly. Yeah, and that's cool that you're seeing so far ahead. So that is going to be equal to your delta y as well. Delta y. So in order to solve for your true factor, let's write it over here to the side. And it's really hard to see, but factor is going to be equal to your change in y to the power of the reciprocal of delta x. And that's hard to see unless you see an example. But there's the formula. So this is to the power of 1 over delta x. And I can try to make my triangle a little bit sharper. Delta x. And that, I'm slightly regretting writing these formulas because that looks really confusing. It looks like Chinese to me, but it'll make sense once we see an example, hopefully. Yeah, Kira.
I'm still like the equations where you went like delta x times difference, but I thought you were replacing the difference with delta x, but you're replacing a with delta x.
So remember that difference is how much I'm moving to get from here to here.
So you still leaving 4 there even though you crossed it out.
So, where's that? I'm missing values in the table. I can't just jump from 2 to 4 because I won't know the true difference. A real table, if I had every single stepping by 1, it should go 2, 3, 4, 5, 6, 7, 8. I'm missing values. To account for those missing values, we have to do this method. So that difference is this true difference is stepping by 1 each time. This true factor is multiplying after I take 1 step in the x direction. Just 1 and 1. I can't jump 3 each time. That leads to some weird math. Yeah.
So the goal of that is to find the difference because we don't know the difference.
Exactly.
And we don't know the factor.
Yeah. We thought the difference was 4, but that's assuming that you step by 2 each time. The difference is only when we step by 1 each time in the x direction. The factor is only when we step by 1 each time in the x direction. I promise that there is a shortcut if you're really, really confused, but I really want to show you where all the math is coming from. All right, so this is going to be one of the harder examples first, and then the easier example second, I think. I'm pretty sure, yeah. Okay, so example 1. We have rabbits. They're on an island. It looks like they are procreating and making more rabbits. So we need to figure out, first, is it linear or is it exponential? And then we need to then choose the right equation. So you can tell that, hey, these two are linear. A and B are linear because they're doing something plus, something times, something else. It matches this form for our linear function right here. It looks like that. And then the second 2 equations look like exponential equations where it's the initial amount times our factor to the power of the variable. All right, so first, we have to figure out, is it linear or is it exponential? This is very similar to what you did in 8-1, your very first lesson. So to find that out, what do we do? Charles?
I think that it is linear because if you multiplied 127 by 2 or anything higher, you couldn't get 153.
Okay, yeah, so it has to be linear. So if I'm linear, then what am I adding each time? Let's try it out. So we have calculators for this, so I'm going to use them as well. 153 minus 127, and we get 26. So to get from here to here, we'll say plus 26. And to get from 153 to 180, what is that going to be? 20 plus 27. Oh yeah, they're about the same, yeah. And then to get from here to here, I do plus 40? Whoa, what's happening here? Did I mess up somewhere? No? What's up, Wyatt?
I think it's exponential.
You think it's exponential? Why is that?
Because it's not increasing by a constant rate with addition, so I think you have to use multiplication.
Yeah.
Even if it is smaller than 2, but it is greater than 1, so it'd be 1 to a decimal. Like
Yeah.
1 to 1.
Yeah, and you're right. If it doesn't look like these are the same numbers, then it has to be exponential. And then you also have the correct analysis. It might be a number that's a little bit like in between 1 and 2, a decimal. So how are we going to figure out what that ratio is, what that factor? Does anyone remember all the way back from 8-1? And I will tell you. So I'm going to divide the second by the first. So again, our shortcut for, I'm going to call this in quotes difference because it's not the true difference. So put in quotes difference. It's not the true difference, but it's second minus first. And then in quotes, our factor, not our true factor because we'll have to play with it a little bit, is equal to second divided by first. So that's what we were doing here. We're doing 153 minus 127. We are doing the second number, 153, minus the first number, 127. That's how we were finding all of these differences over here. So I'll put, these were our differences in quotes. And these are going to be the factors. And I'll put quotes around that because it's not really the factor. How am I going to do the factor between 127 and 153? What operation do I do? Sorry, Charles, you've participated like 3 times. Got to get someone else in here. What is the approximate factor to get from 127 to 153? Using your formula that I just gave you.
Do you use a calculator?
Well, yeah, tell me what to do on the calculator. Kira, question?
Yes. So the difference is like 26, 127, that stuff. And then the factors are 127, 153. Those are the factors.
No, so I'm just saying to get from 127 to 153, I had to add 26. To get from 153 to 180, I had to add 27. The question I'm asking now is what do I need to multiply now to get from 127 to 153?
Then why did you put difference in factor?
So we don't know if it's linear or exponential. This was if it was linear, which it clearly isn't because these are not the same numbers. These could be the same number, but we don't know. We have to find them out. So we have to try both of them. Yeah, Esha, talk to us.
So in the calculator, you should put 153 divided by 127.
Yep, and we get about, I'm going to round that to 1.2. So our factor here is 1.2. What about this one? How would I find the approximate factor from 153 to 180? What would I do, Wyatt?
Would you divide 180 by 153?
You would indeed. And I get about 1.76. 1.76. That's really weird. Oh, 1.176. I missed that. I'm going to round that to 1.18. Sorry, I can't read. 1.18. Oh, those are looking kind of similar. That's good. Yeah, Charles?
I say it's no solution because on both sides, no, you can't. It's
Oh.
not a constant amount.
Okay, yeah. So it looks like neither is a constant amount. Unfortunately, that's not one of the answers.
Oh,
Does
those
that
are the
have to do
answers.
with-
Those are the only possible choices that we have. It has to be one or the other, which means it's not going to be perfect. And this is one of those weird areas that I've gone on my tangent before. Math, when I apply it to the real world, is messy and it doesn't work all the time. And this is a case where that's happening now. So how do I get the approximate factor between 180 and 220? What operation do I do, Emma? Which one goes on top? Yeah, 220. 220 divided by 180. And I get 1.22. So this is times 1.22. And then finally, I'll do the last one, 265 divided by 220. And I get 1.2. So this is times 1.2. And we can see, yeah, it's not perfect, but it's about 1.2 on the right.
A lot closer than the.
And hey, check it out. This is one of the answers, 1.2. That is one of the factors. All right, so are we done? Like, we figured out it's exponential, right? We figured out that the factor is 1.2, so can't we just choose C and be done?
Because that's not the true factor.
It's not the true factor. Which means, here's your shortcut. Find it, it's the other one. The answer is D. But let's figure out why.
Find it, it's the other one.
I swear, that's the shortcut for these multiple choice questions. Unfortunately, if I gave you a free response, you would be lost. And I'm not going to give you a free response because you're not in Algebra 2 yet. This is an Algebra 2 problem where you have to solve this by hand. Multiple choice is when I can leave this with Algebra 1. So how do I know it's 1.1? Well, I use our formula up here. So I'm knowing that I'm going to be an exponential, so I'm going to use this formula right here, the factor. How do I find the factor? Well, factor to the power of x is equal to delta y, or I can just come over here and say, no, let's do this. Yeah, because I want to explain where this formula came from. So let's say factor to the power of delta x. So I'm going to say, over here, factor, I'm going to call it f for factor, if that's cool with you guys. Factor to the power of, how much am I changing with my x? What's my delta x with a quiet raised hand? Emma again?
2.
Yeah. Factor to the power of 2, because I'm changing by 2. I'm adding 2 here, plus 2, plus 2. So factor to the power of 2 is equal to my change in y. That's what it says right here in my equation up here, my change in y. And I'm changing y roughly by about 1.2. So I'm going to say about 1.2. Okay, if this is my equation, f squared is equal to 1.2, and I want to solve for f, what do I do to both sides? Charles?
You divide it by delta x.
Not quite. To undo to the power of 2,
You square root it.
square root both sides. Square root that side, square root that side, and I get f is equal to, and I have to get on my calculator here, SQRT of 1.2, 1.095, which rounds up to 1.1. And hey, check that out. That's the answer. 1.1 was the true factor.
Wait, go back to the math, please.
All right, this is where I'm going to go on a brief tangent where you can totally tune me out. You do not need this, but if you're interested in what would happen with harder cases, which might occur on the homework, and you really want to know what's going on without using the shortcut, this is what's really happening. What if I just changed these values and I was increasing by 3 each time? It went 0, 3, 6, 9, 12, etc., etc. That would mean that our equation over here only has to change like this. Our equation could have been, so this is, let's do an if section. What if I had f to the power of 3 is equal to 1.2? How would I get rid of to the power of 3? What?
You cube root it.
I would cube root both sides. Cube root, which is the same thing as saying 1.2 to the power of 1 divided by 3. Have I taught you fractional exponents yet? Ooh, okay. Maybe I should have stayed away from that.
Actually, I think so. 'Cause it would, oh wait, no, that wasn't
You
good.
haven't taught us like how to solve.
Okay. Then I will leave that as the cube root of 1.2. And then there's no way to do that on the Spotlight search aside from using fractional powers. So I'd have to come over here to my calculator. And the way that you do cube roots, they should have like an n to the power of, so this thing, and I can choose whatever. I can do 5 root or the 7th root or 4th root. Like I say, the cube root of 1.2, and that's 1.06.
So we 1.06.
So yeah, the factor could have been 1.06 if I was increasing by 3. Kira, question?
Okay, so why did you do factor squared? Why did you square that?
Yeah, so can someone else, why did we have this 2, f squared? Charles?
It's the formula, or that's delta x.
So delta x over here,
Oh, I see.
and there's our formula, yeah. That was the hardest question that I can give you, by the way. I'm going to move on to an easier question. All right. Our final example. Example number 2. We have peanut butter being measured by Miss Leslie, and she says, okay, peanut butter in ounces over the course of a week and a half, or almost 2 weeks, looks like this. It's going down. So we ask ourselves, is it linear or exponential? Well, let's go ahead and figure this out. So I'm going to go on the left-hand side. I'm going to say this is the difference, in quotes. And then this is going to be the factor, in quotes. All right, so how do I move from 345 to 313 by adding something? Or how do I move from 345 to 313 by multiplying by something? Ulysses.
30?
Uh,
What 32 I mean?
32, what do you mean by 32?
Like add 30.
Not, so I agree that if I went from this direction, I would definitely be adding 32, but in the other direction, I would be, exactly, subtracting 32. So I should probably change that to minus 32. Thank you. And then someone else again. How do I get from 313 to 285? I'm going to be subtracting something else. And again, if you don't know how to do that, you do the second minus the first. I do 285 minus 313. And I get, Charles?
Minus 20.
Negative 28. Or minus 28. Uh-oh, this might not be good. Let's try another one. How do I get from 285 to 255? What?
Minus 30.
Minus 30. Oh, these are actually kind of roughly in the same ballpark. That's looking good. What about 255 to 227? Emma? Minus 33, like that? Yeah, I think that's right? Yeah, nice. Thank you. Is it 28?
It's 28
Yeah,
minus 28.
Oh, darn. Sorry. Minus 28. Okay, so if we had to average these, what would they look like? Average around 20, 28, 29. What does it show down here?
30,
Ooh.
I think.
30.
Oh yeah, so they're trying to approximate it using 30. And I mean, 1 is above, 2 are below, so I guess 29 would have been a more accurate model, but we'll go with 30 for now, I guess. Do you guys think it's linear or exponential?
Well, we don't know what the exponential like decay is.
Okay, yeah, so let's go ahead and find these. So how do I find the factor? What do I do on my calculator? Kira?
Maybe like a 13 divided by 345.
There it is, and I get about 0.91. This is about 0.91. All right, and I'll do these really quickly for us to get through this. So this is 285 divided by 313. That's 0.91 again. 0.91. And then to get from 285 from 313, that's also 0.91. And then 227 divided by 255, that's, 0.89.
Still really close.
And that is because I have made this problem. Khan Academy, they're never that close. I apologize. I would say you could model this one either way because they're so close to one another. I would say to me, it looks a little bit more exponential than it does linear.
Yeah.
Yeah, let's use our shortcut method on this. Let's assume it's exponential. I know this is a bad problem, and I apologize. It could have been linear. If you have an argument for linear, I would believe you. It looks like our average over here is about 0.9. So 0.9, right? The answer is C, right? No, the answer is actually
B.
D. Done. I mean, that's a shortcut. You choose one, and then it's always the other one because we have to, in this case, we'd have to cube root it because our delta x is changing by 3. So if you want to do it the long way, you can say, hey, the factor that we're looking for needs to be to the power of 3 because this is your change in x, and that is equal to 0.9. And hey, if I do that, oh, I can't do cube roots on here unless I use fractional powers. I have to come over here and say, hey, what's the cube root of was it 0.9? Yeah, 0.9 is 0.965? 0.96. There it is. Just to have very complete notes, I'm being very thorough. What if I assume that it was linear? How would I find the factor? Or how would I find the difference? I do 3 times the difference is equal to negative 30 here. And then I divide both sides by 3 and I get difference is equal to negative 10. And hey, that's where the negative 10 came from.
So B or D could
B or D. I'll circle both of them. Both of them should be technically correct. Yeah. The Khan Academy will never have them that close to each other. I will fix that for next year. Sorry about that. All right, that concludes the notes. Any questions? There's probably lots of questions. Any questions that I can answer? Yeah, Larissa.
Why would you multiply the difference by 3?
Great question. Someone else answered. Sure. Kira. Because Kira had a similar question.
So on the time side, you're always going up by 3, like 0 plus 3 is 3.
Oh.
And so,
Oh yeah, that's just, oh yeah, yeah.
Yeah. Any other questions? That was a great question. All right. Give me a fist of 5 on how you can you determine whether the data is linear or exponential? You guys are at 4 or 5. Those are higher scores than I was expecting because that was a bad second example. All right. Cool. Thank you.